way in which you would use this to assess the phosphorylation state of a protein. So once again, we're going to use the same protein 1-coded donor bead from the last slide, but now we're going to ask the question, to what extent is this protein tyrosine phosphorylated? So the way that we would set up that assay is we would buy an acceptor bead that is pre-coated with an anti-phosphotyrosine antibody. And so when the protein is phosphorylated, we're going to you can see proximity. The two beads are going to come in proximity to one another. When it's not phosphorylated, they will not. The advantages of AlphaScreen are, of all the things we talked about, it's got the highest sensitivity and the highest dynamic range, and also the lowest background. It works at very low volume, so when I was first showing you the plates, it's tough to run assays in that 1534 well format, less than 20 microliters. AlphaScreen is one of the best methods to use when you're at that really high plate density. There are very flexible options. Like I said, it's kind of plug and play. So there's a lot of different types of these donor acceptor beads that you can just buy from a vendor. And then the disadvantages are that same thing, is that while there's so many things you can buy, you are so limited to analytes that are pre-tagged with something that's going to stick them to that bead. And another consideration is that the placement of these tags is important. So this right here only works if the antibody binds the protein on the opposite face of the protein from the phosphorylation site. Imagine if the phosphorylation site is right next to where the antibody binds. This is not going to work because it's going to be sterically or physically impeded from interacting with one another. Same thing on the bounce back to the previous slide. Basically, this only works if these two proteins interact with each other on this face. If we need this face of protein 1 to react with the other, to interact with the other side of protein 2, again, the attachment of this protein to the bead is going to block that binding to that aggregation. So there is some sort of rational design involved in setting these assays up. Okay, so we'll summarize now the strengths and weaknesses of everything I talked about. So basically, with these assay technologies, you have sort of a spectrum going from fluorescence intensity, which is super simple to implement, but has a high propensity for interference from the compounds you're screening. Then on the other end of the spectrum, you have luminescence and an assay like FP that are far less susceptible to interference from the screening compounds, but are also much more complex to implement. So it's basically a trade-off. The more complex it is, the more robust the assay is going to be. And then the TR FRET and AlphaScreen and FRET assays are sort of middle of the road on these two extremes. All right, so now we'll jump into the key principles of designing an assay. And I will point you to this NCBI library. This is on the NCBI website, the Assay Guidance Manual. A lot of this is lifted from that. It's a really great resource. I don't have time to cover everything that's covered in this manual, but if you are looking to set up an HTS screen, this has tons of protocols, standard operating procedures, things like that, that you need to worry about. So highly recommend that. Okay, so let's say you want to hunt for a biologically active molecule that acts on your target of interest. What are the most important questions to ask to start? The singular most important question is, are there commercially available kits that are able to be applied to this target? It is always going to be preferable to buy an assay kit than it is to develop a new assay from scratch. You do not want to reinvent the wheel if such a kit exists and can be purchased. So there are tons of kits that you can purchase to assess kinase activity, phosphatase activity, phosphodiesterase activity. Any system where you know that ATP, AMP, GMP, GP, etc. are produced, there are off-the-shelf kits that will measure the production of those molecules. They have instruction manuals, they're very detailed. There's tons of QC that went into the production of the kits, and you can trust that they're going to work. And we'll see that there are a lot of pitfalls in developing a screen, so you just really want to avoid that at all costs if you can. That said, a lot of times in research, there is not a kit. We were doing something groundbreaking, studying something new, and we can't purchase a kit to ask the questions that we want to ask. So the next question is my assay that I'm running truly amenable to HTS? And you have to really look at this really critically. So many things that are acceptable in a biological assay that is publishable, that is rigorous, that you can reproduce in multiple replicates, are still going to cause problems if you try to port them into an HTS setting. So this is just a little representative list of things that are going to cause problems for you, whereas they're really a non-issue in a low throughput in a single compound setting. So assays that have a narrow dynamic range, assays that have a very high background, assays that require excessive manipulations or wash steps, assays that use probes or tracers that have a very low affinity for the protein target of interest, assays that require a transient cellular transfection versus a stable one, enzymatic assays where the substrate concentration is at or below the Km, so you want the substrate concentration for enzymatic assays to be quite high, and then assays that do not have a well-defined positive and negative control already. So a lot of these issues can be overcome in a single compound or in a low throughput setting by doing lots of replicates. And one of the main issues in HTS is that you're really limited. You're running a very large screen, and you're really going to be able to test these compounds either 1 or 2 times, maybe a maximum of 3. You're not going to be able to get around some of these issues with more replicates in HTS. Let's touch on the idea of positive and negative controls really quickly. So this seems a little counterintuitive. It's a little bit of a chicken egg problem, because if you're running an assay to search for a biologically active molecule, there may not be a molecule that has this activity that already exists. But that said, without a positive and a negative control, it's impossible to validate the assay, and an unvalidated assay makes it very difficult to identify what is a hit or what is just noise, because there's always going to be some degree of noise in any experiment. And this validation process, which I'm going to talk about in more detail, helps give you confidence that yes, this is a real activity versus this is just experimental variance. And so positive and negative controls are critical to help you ascertain that. Negative controls are super easy. So basically, when we transfer the screening compounds from the compound plate into the assay plate, they're usually dissolved in DMSO. A very small amount of DMSO is a solvent, and you use that to do the liquid transfer into the assay plate. And so the negative control is just going to be a blank DMSO with no compound in it. The positive control, again, is more tricky. So ideally, it's a known inhibitor. And there's tons of cases where you're screening for an improved inhibitor of a compound that has a known inhibitor that is flawed in some way. It's not druggable, it's promiscuous. There's tons of situations where you are designing a screen where a known inhibitor exists. But if you are in the unfortunate situation where a known inhibitor does not yet exist, the positive control can be basically no enzyme, so this is an artificial control. But you want to keep in mind that artificial control assays have no biological relevance, and the results or the hit list you get from an artificially controlled assay could be worlds different from the same assay run with a biologically relevant control. So one solution is to run an artificial control assay to identify maybe a subpar inhibitor, and then use that compound as a positive control then for the next assay. Another thing that you need to select at the onset of your assay is your probe molecule. This is whatever entity is in that well that is giving you your readout. It's glowing, it's changing color. In HTS, this tag it's basically something, either a biomolecule or a small molecule that's tagged. In HTS, again, the tag is usually fluorescent, most commonly, and so you can have any flavor of fluorescent reporter. It could be a small molecule. So I showed you a fluorescence polarization assay where there was a fluorescently tagged small molecule that was getting displaced. That was the probe in that setting. You can also have fluorescently tagged peptides, RNA, DNA, proteins, and cells. And the most important thing to keep in mind when selecting a probe is that the placement of this tag is important. You do not want the attached tag to impede whatever it is that the untagged protein will typically do. This is an example of the actual chemical structure of a tagged small molecule. So this is galvanomycin, which is an inhibitor of the protein heat shock protein 90. And this tag works because this probe works because the fluorescent FITC tag is attached on the region of the molecule that when it's bound to HSP90 is displayed out into solvent, into space. If we were to attach the tag on this side, the probe would not work because this region of the molecule is actually tucked into the binding site of the protein. So it's important to place the tag properly, and sometimes it's trial and error. You might have to make a number of different tagged probe molecules and test them to see which ones actually do seem to bind the protein and which ones are blocked from binding by the placement of the tag, by the unfortunate placement of the tag. In terms of choosing the fluorophore, apologies, this is super easy to see, but basically, this is a range of different commercially available organic dyes that you can buy with various reactive handles on them for attachment to small molecules or proteins. And so basically these dyes come in a range of colors from green to red. I would say in the low throughput or a non-HTS setting, these green dyes are super popular. But a really important thing to keep in mind in HTS assays is that it's much better to use a redshifted dye. And the reason for that is that in HTS assays, the screening molecule concentration is generally in the micromolar range. And typically, the probe concentration, say like in an FT assay, the probe is present in a nanomolar concentration. Now, most organic small molecules, I have a collaborator who jokes that every kit looks like a couple of benzene rings with some carbons and nitrogens in between. And those benzene rings absorb UV light, basically. They absorb light in the blue-green region as well. And so, if you have a really high concentration of a molecule that absorbs the green light that's produced, it's going to interfere with that signal. So it's better to use a red-shifted fluorophore that has an emission range that's well outside of what most typical small molecules absorb. So you won't see that interference from the screening molecule. So this comes up a lot where you've sort of developed an assay with a green dye, but then it doesn't work in an HTS setting, and the only solution is you do have to switch over to a more red-shifted dye to get the HTS assay to work reliably. Let's go back to the FP competition assay. So some other things to keep in mind in terms of probe selection. If you have multiple probes to choose from, and as I said, a lot of times you are synthesizing more than one probe, and you are then evaluating how well do they engage this protein that I want to study. The two things that you want to use to select the probe are you want to have a better quantum yield is always better, more light produced. And then you also want to consider the dissociation constant for the probe with the target, Kd. So if you have two probes that have the same fluorophore, so they have equivalent quantum yield, the probe with the lowest Kd is always going to be the best. So lower Kd can identify compounds across a wider range of potencies, and a lower Kd is going to require you to actually put less probe into each assay well. And so that's going to, and also less protein to generate a measurable signal. So it's going to reduce the cost of producing or buying both the probe and the protein that you're studying. Because you need, if you're filling hundreds of wells or thousands of wells or tens of thousands of wells with these assay mixtures, the cost of the assay mixture you're putting in does become important, or does become an important consideration. Okay, so let's say you've got your assay, you've picked what detection method you're going to use, you've got your probe, you know it works, and you've designed the protocol for your assay. The next step is to do QC on that assay to ensure that it works reliably and robustly. So if you're miniaturizing an assay, so basically taking an assay from like a petri dish to a 96 well plate or a 34 well plate, you encounter a lot of challenges. So there are challenges just in execution. You're operating with really small sample volumes. You're operating in a very large throughput, so you're doing the same thing over and over again on hundreds or thousands of plates. And you also have significant challenges in interpretation. So trying to figure out what is a hit versus what is just regular noise. And that is impacted by the sensitivity of the assay, the reproducibility of the assay. You get the same results tomorrow that you got today on the same plate. The accuracy of the assay, and an added challenge is the the fact that you are provided with limited data points. You're generally running just in singlet or in duplicate, and that's it. It's too expensive or too resource intensive to do more than that in a given screen. So the way in which you assess whether you have you met these challenges adequately is to do assay validation prior to actually running the screen. So assay validation is critical because assays designed in a basic research laboratory may not necessarily perform the same standards as those in HTS. We just talked about that. And a failed HTS assay is tremendously expensive in terms of both resources and also your time and effort. It takes a long time, so you want to make sure that you get it right once you put when you're actually putting compounds in. So validation is defined as determining the robustness and reliability of the assay before you actually run the screen. It's also super helpful to do this because it helps you troubleshoot. If you follow the validation protocols that I'm going to show you right now, it helps you troubleshoot problems with the assays and also helps you assess QC of the reagents you're using. If there's any issue with the stability of the reagents, you're going to notice it in the validation stage, and it's going to, again, prevent this sort of waste of time and resources and effort for something that is beyond your control. It's an unstable agent. Okay, so reagent stability. So the thing to keep in mind is that high throughput screens are usually multi-day processes. So in light of that, you want to handle and store the reagents and controls over these multiple days according to the manufacturer's recommendations. You always want to minimize freeze thaws of both your reagents and then the compound stocks, your compound plate that has these compounds dissolved in DMSO. And the reason for that is just when you do it, when you pull something out of the freezer and it warms up, you put it back in the freezer and it cools down. You do that over and over again. I don't know, I'm an organic chemist. I don't know if you guys took organic chemistry, but a recrystallization is having something that's dissolved in a high concentration, heating it up and cooling it down. And that often induces precipitation. Also, it's like similar to like when you make fudge and you accidentally heat it up and then it accidentally crystallizes because there's a little bit of crystalline sugar in there, for example. So repeated freeze thaws are going to cause the compounds to drop out of solution. Typically, you want to do less than 8, but ideally, in a high-throughput screen, you don't really want to be doing more than 2 or 3 freeze thaws of your compound stocks. And then you also similarly want to minimize the freeze thaws of your reagents as well. So a way to get around that is that it's good to aliquot for daily use. If you know that you're going to be running the screen over 5 days, you take your parent reagent and you, on the first day, divvy it up into 5 portions. And freeze each of those portions, and you just take it out one-time use, and then you're done. You're not putting anything back in the freezer if you operate with that mentality. You also have to make sure that your assay tolerates the presence of DMSO. So it takes a good amount of DMSO to get those compounds into the assay mixture because most organic small molecules that you're screening are not really soluble in water. So you need a little bit of DMSO to transfer them in. Generally, you want to make sure your assay tolerates up to 10% concentration DMSO. However, a cell-based assay, the cells will not be happy with 10% DMSO, so the limit is 1% DMSO there, but you want to make sure that the assay still works when 1% DMSO is present. And then you also want to test the stability of all these reagents you're using, so it's best to do head-to-head comparisons of a fresh aliquot versus something that you made a week ago or 2 weeks ago to make sure that they behave similarly. And if they don't, you know that you need to make everything fresh, the data, basically. You also have to select a screening concentration. So probably the 2 most typical concentrations for high-throughput screens are 10 micromolar or 1 micromolar. And basically, it's a kind of a rule of thumb that the higher screening concentration you have, the more hits you're going to see. Okay? So screening at higher concentrations leads to more hits and fewer missed opportunities. But there are some negative aspects of screening at higher concentrations. There's an increased chance of cytotoxicity in cellular assays, so the compound might kill the cells at high concentrations, whereas it might have your desired effect at a much lower concentration without killing the cell. You would miss that. You have an increased chance of the types of compound interference we've talked about, the interfilter effects, the fluorescence quenching, things like that, when the compound is present at a high concentration versus a low concentration. And then once you hit 10 micromolar and above at that maximum 10% DMSO, you start to hit the limits of solubility for a lot of these screening compounds. And so at very high concentrations, a lot of the screening compounds are going to either precipitate or they're going to aggregate. And we'll talk about aggregation a bit more in a second. But they're basically going to drop out of solution, and And so, number one, if they are active, you're not going to be able to see that activity because they're not dissolved. And number two, sometimes these aggregation effects can actually lead to something that looks like a false positive. So you really don't want to go too far above 10 micromolar in your strains. Yeah?
So when people are designing these, do they usually prioritize technical duplicates, or do people tend to do, like, not do duplicates but try 2 doses instead, or how
yeah, so one of the most important considerations is how much time and reagents you have. It may be that you just do not have enough probe or enough protein produced, for example, to do duplicates. But duplicates is always better than singlet. And so, actually, the next couple of slides I'll kind of show you. There is one of the equations that you do for QC, which is similar to a standard deviation type calculation, but it's specific for HDS. Actually considers the number of replicates you plan to run. And so, if you run QC on your assay, it may be robust enough that you can just do single kit, and that's always best because it's less time and it's less effort. But typically you're not that lucky. The assay is not robust enough, and you do need to do 2 replicates ideally. So there's a lot of different factors feeding into those decisions. You kind of have to look at the big picture when you're designing that. And I would say I myself don't run screens, but I work with a lot of people. And you see a whole wide range of decisions being made, and sometimes I don't always agree with the decisions that are like that. Wow, you should not have screened the compounds at 50 micromolar. That was a waste of time because everything precipitated in. And so, but that was a decision that they made, and so it's sometimes you just have to kind of roll the dice and get lucky or make the wrong call. Okay, so you selected a screening concentration. You also have to select a well plate style. So there's the well plate sizes and densities, the 96, 34, 15, 36. So that's going to depend on your liquid handling capabilities and the miniaturizability of the assay. Some assays just only work at 96, and then once you go to 384, they're cracked. So you're stuck with 96 well plates, and that's that. You kind of have to test that on the fly. And then the plate style and color is going to be important. So I have shown here just a clear, plain plate. But plates do come in different colors and styles. So translucent plates, these clear type plates, are best for holding compounds. And they're also good for anything where you have a change in color, like the UV absorbance assay. It's best to put your compound storage in these plates just so you can see that the compounds are actually in there. However, if you're doing a luminescence or a fluorescence-based assay, you do not want your well plates to be clear. You want them to be opaque because you do not want the light from one well to be shining into its neighbors, right? So in a luminescence setting, it's best to use an opaque white plate, and in a fluorescence setting, it's best to use an opaque black plate. Now these plates also are going to have different options in terms of what does the bottom of the plate look like. If you are running an assay where you are shining light on the top and reading from the bottom, the well bottom have to be clear, right? But if you are shining, the fluorescence assay where you're doing fluorescent light in and then reading also from the top as well, you do not want the bottom to be clear because you don't want to lose any light to the bottom, right? So you want an opaque bottom for top detection. And then the well bottom shape is also important. So again, in the compound plates that hold the compounds, the best type of plate is the V-bottom plate, as that's going to minimize dead volume. But then in these actual assay plates, you're typically going to be deciding between a flat bottom and a round bottom. A flat bottom are pretty much mandatory for anything that's read-through because you want it to be uniform and flat all the way across the bottom of the well. And in general, most of the assays you see are going to be running flat bottom plates. Round bottom plates, though, are best for if you're handling cells, if you need to wash the cells. You're likely going to be working like a 96 well round bottom plate. But more frequently, you'll see flat bottom plates as sort of the standard. And then, so liquid handling. Okay, so this is where resources come into play, right? So if you're running an assay, you typically have a multi-channel pipette or a single-channel pipette. And then, if you're doing a low throughput or a medium throughput screen of hundreds of compounds or dozens of compounds, you may do something that looks like a high throughput screen, but you're using sort of a multi-channel pipette to transfer reagents or to transfer the compounds into the assay mixture, basically. That's the main liquid handling you need to do. You need to get your reagents into the wells, and then you need to get your compounds into the wells. And so if you're doing 25 compounds, it's not a big deal, right? You can use or 24 compounds, it's like 3 pipetting actions with an 8-channel pipette. If you're doing 50,000 compounds, that's a lot of pipetting, even with a multi-channel pipette. And you don't necessarily want to be doing that. So once you're in the large number of compounds, you need to use robotic liquid handler for that automation. So there's a number of different types of liquid handlers. Some transfer compounds using pipettes. So this is like the equivalent of a multi-channel pipette that has 96 different pipettes loaded onto it. It can pick up 96 compounds at a time, sort of stamp them into the plates. There are also pin transfers, and then there's also acoustic dispensing, where you have a little, it's basically a little sonicator, a tiny little pinhead sonicator that basically pops a little drop of liquid out of the well up and into another plate, basically. And this is often used for the very, if you're operating in like a 1 microliter 1536 well plate, you can't pipette at that point. They don't make pipette tips that small, and the capillary action is going to prevent the full dissolution. So you have to use these more sophisticated acoustic dispensing mechanisms to dispense like the nanoliter or the single-digit microliter volumes of compounds or of reagents, basically. But what you use here is it really totally depends on your resources. A lot of people don't have access to these fancy robot liquid handlers. It's great when you do, but you don't always. And so sometimes you may be running a screen with a multi-channel pipette. In that case, you really have to limit the number of compounds you're assaying because it's just not practical to be hand pipetting so much stuff. Okay, so assay validation. Why assay validation is important? For all assays, you want to be confident that the assay has sufficient range and reproducibility to avoid false positives and false negatives. And you want to make sure that you can compare 2 results, 2 wells, well to well. So is an inactive compound on the upper right-hand corner going to look exactly the same as an inactive compound on the lower left-hand corner of this plate to plate? So is well A1 on this plate going to look exactly the same as well A1 on the next plate that I run? And then day to day, if I take the same plate and I run it today and then I run it on next Monday, am I going to get the same results? For biochemical assays, it has the added benefit of ensuring that everything's stable and behaves as expected. So we talked about this, your sort of reagent QCs. And then for cell-based assays, this also helps you evaluate a lot of, so we've talked about all the choices you have to make. For cell-based assays, you have to make even more choices. You have to choose what cellular line you're going to use. You have to choose, how many passages of cells, how many cells do you bank to see how long do you apply the compound to the cells. These are all variables that are going to affect the outcome of your assay. And the assay validation stage is a much better time to be figuring that out than when you're actually running the screen or after you run the screen. So all these factors can cause extreme variation if they're not properly selected and controlled. Okay, so how do we evaluate assay QC? So when for a lot of analytical methods, one of the ways in which we determine whether this analysis is good or bad is using signal to noise, right? In HTS, signal to noise is not a helpful QC metric. These graphics kind of try to show you why. Basically, the goal in a high quality, high throughput screen is to enable you to easily pick out hit compounds from the field of inactive things. Most of the compounds are not going to be active. A few compounds will be active, and you want to be able to figure out which ones those are really easily. So these 2 plots have an example of 2 different assays where the circles are your screening compounds, the squares are your negative controls, and in the assay on the left, you don't have a really great signal to noise compared to the assay on the right. So the signal to noise in this assay is 12, and the signal to noise in the assay on the right is 27. However, there is way more variance in the assay on the right than the one on the left, right? So if for an inhibition assay, a hit's probably going to be in this this big amount of white space that doesn't have any signals in it. Whereas in this assay with all of this variance, it's going to be really difficult to pull a hit out, right? You have a very narrow window in which there aren't any. Is this a hit? Is this just noise? It's hard to tell. So even though you may have an assay where the signal to noise is low and the signal to background is low, as long as the data doesn't vary that much, you're still in good shape. You can have a very high signal to noise, very high signal to background. Too much variance, you're not in good shape. And so, how do we quantify this? How do we measure the good scenario versus the bad scenario? We do that using a calculation called the z-factor coefficient. So the z-factor principle states that the lower the variation in the assay, the more confidence that a hit is real. What we just talked about in the previous slide. So if you can calculate the z-factor for the screen itself, or you can calculate it before you run the screen. Before you run the screen, it's called the z-prime factor. So this is a z-factor calculated in the absence of screening compounds. And then the z-factor is almost the same equation, but it's in the presence of screening compounds, basically. So what you're going to do is you're going to run several plates, not the full number of plates that you would run in a screen. We're talking now about calculating the z-prime factor. We're going to run several plates that are just populated with positive controls and negative controls in this case. And you'll gather a bunch of data points, and you're going to do a little bit of math on those, a little bit of statistics on those data points. So you're going to take the mean, you're calculate the mean of all of the positive control signals and the standard deviation. You're going to calculate the mean and standard deviation of all the negative control signals, and you're just going to plug them into this equation. It's pretty simple. So this is before the screen. You can also do a similar calculation after you've run the screen to determine the quality of the actual executed screen itself, and it's very similar. All you're doing is, instead of plugging the mean and standard deviation of the positive control into this equation, you're doing the same values for all of the collective library compound, all the screen compounds, basically. And what you choose here in this negative control spot is, it depends on whether this is an activation screen or an inhibition screen. So if it's an activation screen, this is going to be the positive control signals, and if it's an inhibition screen, this is going to be the negative control signals for these two components of these equations. So again, the z-prime factor is going to give you a quantitative assessment of the overall quantity of the assay before you've screened any compounds. And then the z-factor is calculated after the screen, and it tells you the overall quality of the executed screen. So you'll plug these values into these equations, you're going to get a number. The perfect assay is going to have a z or z-prime factor equal to 1. So all of these guys, there's going to be no variance, and this is all going to basically calculate out to 0. So it's 1 minus 0 is 1. An acceptable assay needs to have a z or z-prime factor greater than 0.4. As long as it's greater than 0.4, you have pretty high confidence that you're going to be able to identify hits from the field. If it's below 0.4, it's poor quality. You may be able, you'll still be able to kind of make out hits, but there won't be as high confidence, and you'll have more false positives. And then, if this number is less than 0, basically all the signals coming out of the wells are essentially random. Screening is impossible. There's no way of telling hits from noise if that's less than 0. There's a serious problem with your assay, and you need to retool it in some way. Now, if you do all this analysis and you pre-analyze your screening, you determine that your z-prime was fantastic, really close to 1, but then you execute the screen and you find that the actual z-factor post-screen is close to 0, it's likely that the problem here is the compound library you're using. It's likely hurting the assay quality. You may need to check the compound library for interference. It might have, say, you're doing fluorescence, and the library might be filled with fluorescent compounds. That could be a problem. Or you may just be operating at too high a concentration and you need to lower it down, and then the z-value will improve. The best way, or the best practice for doing this pre-screen z-prime factor calculation is to do it in the context of this experiment that's called the Interleaved signal test. So this test, and this protocol comes straight out of the assay guidance manual. This test tells you 2 things. It's going to help you to calculate the z-prime factor. So it's going to generate all that data you need to run statistics and plug into those equations. And then it's also going to help you understand the plate uniformity. So another key question is that you want to ascertain before you run the assay is, ideally, is how much does the signal coming out of a given well depend on where on the plate that well is? Because sometimes the position on the plate can play a factor if there's a flaw in the screen. So basically, the way in which you're going to run this assay is you're going to set up 3 plates for yourself. And this requires a known inhibitor, a positive control. So the 3 plates are going to be plated with columns of compounds in this pattern where you have a high concentration, a high signal, so no inhibitor, a medium signal, so that's going to be the inhibitor at its at its half maximal concentration, it's EC50. And then the minimum signal is going to be obtained when you've completely swamped with inhibitor, so the maximal effect concentration of that inhibitor. And so you play high, basically red, blue, yellow, blue, yellow, red, blue, yellow, red, yellow, red, blue, yellow, red, blue. And then you run these 3 plate patterns on 3 successive days. If you have already validated the assay in the past, 2 days is okay. But the first time you ever run a new HDS, you're supposed to run these 3 plates on 3 successive days. And that's going to generate a lot of data points. And you're going to plot those data points. So you're going to do a lot of math, basically a lot of QC math. I'm not going to go through this, but you're basically plugging all these values, calculating mean, standard deviations, plugging them into equations, and just doing checks to make sure that all these values are within a certain threshold. So I'm going to skip through this for time. And then you're going to, after you've validated that all these numbers are what they should be, you're basically going to generate what's called plate uniformity plots. So for every plate that you run, you're going to do 2 scatter plots. And each of the scatter plots is going to have basically the well number on the x-axis and the response for that well on the y-axis. And the difference between the 2 scatter plots is you're going to number the plates differently. In the first scatter plot, you're going to number the plates left to right, so 1 through 12, going down the plate. And then in the second scatter plot, you're going to number top to bottom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. You're going to look at those 2 plots, and they should look something like this, basically. So that first plot is going to have clusters of signals for your high, medium, and low signal. And what you want to see is that they are all roughly linear for each of the types of signals that you see in both plots, basically. So this is very nice. Basically, all the signals, like on the left-hand side of the plate, are pretty much comparable to the ones on the right-hand side of the plate. What you do not want to see is this type of drift, where you can see that as you go across the plate, the signals are progressively increasing, and every one of these wells has the same thing in it, so they should, in theory, be equivalent, right? And so it's more of a stair-step pattern in the other type of plot. So this is an indication that you have some sort of drift happening going from left to right across the plate. You can also use this to test for edge effects. So this is a phenomenon where something different happens in the perimeter wells of a plate versus the ones in the middle. And so the pattern that you would see if you're experiencing edge effects is that you have these isolated high or low data points in this sort of pattern. What you're seeing is basically all of the first column is high, and then these isolated edge ones are these 1, 2, 3, 4, 5, 6. And you can see that pattern in both types of plots. And so if you see this in your plate uniformity analysis, your assay suffers from edge effects. So, what are edge effects first? So, well, actually, let's start with drift, because that's the order I was going to talk about. So, the material drift, so it's like sort of creeping up left to right across the plate. So the most common cause for material drift is gradient zones that are caused by your reagents not being homogeneous. So if you have a well-mixed reagent mixture, you're pipetting it into the plate, you should be getting the same concentration and amounts of everything in every well. But if your reagents are not homogeneous and start to settle over time, and you're always drawing from the bottom of the well or the bottom of the tube, the first columns of the plate are going to have proportionally more stuff, and then the right-hand side columns are going to have less. So if you see that kind of drift, that's the first thing to check. How homogeneous is the solution that you pipetted into the plate? This can also result in actual manufacturing faults in the plate. And then in a cellular assay, you can have similar issues with cell banking and handling if you didn't steam the plates well enough, or handle them well enough as you were applying them to the plates. Now going back to edge effects. Edge effects are also very common in cellular assays. And this mostly have to do with the fact that the outside wells are going to experience things a little bit differently from the inside wells. So temperature is one thing that's going to be different, right? The outer wells are going to just cool and heat faster than the central wells because they're not shielded by neighbors. It's exacerbated when you stack the plates on top of one another. They're just more insulated on the inside. And then the outer wells also evaporate more than the inner wells if we have a very long reaction time. This can also occur from failure to sustain even gas distribution over the top of the plate. Now typically, it's tough to troubleshoot this. If you have edge effects, typically you're just going to not run an assay in those outer wells. You're just only going to apply your assay mixture to those interior wells of the plate. So it's good to check for that before you run your screen, right? Okay, so we have like 15 minutes. I'm going to run really quickly through compound libraries and what to do, or how you prosecute hits coming out of these libraries. I'm going to go kind of quickly through these slides, but even though this is my favorite part of the small, I'm a chemist, so I like the molecules, basically. There's a huge variance in the size and types of collections that are out there. So in the pharmaceutical industry, they're running screens on the order of millions of compounds. They have like seemingly infinite resources. They have really fancy robots and acoustic dispensers. And so they have the bandwidth to prosecute these large number of compounds. In academia, we don't have comparatively as much resources. There are some large screening facilities that have the capability of screening like hundreds of thousands of compounds. Here in the Boston area, there's a ICCB screening facility at the Harvard Medical School. In the Longwood area, you can go, it's a fee-for-service place. You can go and pay, and it can help you execute a very large high-throughbut screen with the compounds that they have in stock. And there's a similar screening center on the West Coast at UCSF. We used to have an HTS core here at BU. It no longer exists. It was decommissioned a few years ago. They had 40,000 compounds, and this collection has been passed from group to group who wants to run HTS. I don't know precisely where it is, but if you ever have interest in trying to track down these compounds, contact me and I will help you find those if you ever want to run a screen. I think there is a research lab on the medical campus that has possession of these compounds. The screening core, unfortunately, is no longer attacked. And then you can buy tens of thousands of compounds from a lot of vendors. And then if you're not quite ready to screen hundreds or tens of thousands of compounds, you can buy smaller sets that can still be informative. So you can get just a set of FDA-approved drugs. It's really good for drug repurposing. The NCI offers a lot of screening collections for free. You just fill out a form and they'll send you a plate of 400 natural products or 1,600 diversity compounds. And then this is a little plug for my center, the BU-CMD. We have a screening collection of it's closer to 4,000 compounds at this point. These are compounds that were synthesized by chemists at BU and other institutions, and they differ a little bit from these screening collections. I'll jump into how that is in a second. So basically, the way in which these large libraries of millions or hundreds of thousands of compounds are generated is a process called Combinatorial Chemistry, where you have what's called a conjunctive reaction, any reaction that brings two reagents together and connects them. And so if you identify a reaction like that, and you can purchase a number of this type of building block and a number of this type of building block, you can basically synthesize an array of molecules that explores every possible combination between sets of reagents. These reactions are often run and purified in parallel. It's very efficient, but it also relies on really simple reactions that work really robustly all the time. And that presents some limitations. So the reason for that is from a perspective of molecular complexity. And I have examples, what do I mean by molecular complexity? So I have examples of 4 different painkillers here, and I would say that the 3 painkillers I have shown on the left, aspirin, Advil, and Tylenol, are very simple molecules. The painkiller on the right, hydrocodone, is more complex. It's made by nature, and it has a lot more three-dimensionality. I think I have some of the qualities that make the molecule more complex. Yeah, larger size, more three-dimensionality, and just by nature, compounds that are more complex are more difficult to synthesize. So you typically don't see large screening libraries populated with molecules that look like hydrocodone. It's populated more with molecules that look like this, simpler molecules. Historically, combinatorial chemistry and high-throughput screening have focused on less complex molecules because they're easier to synthesize. And so this is my shameless plug for our center. So the idea behind our screening collection is to sort of complement that and to have a screening collection that's populated with more complex molecules. So this is a smaller size, but we have a lot more three-dimensionality to the molecules in our collection. And then the other nice thing about our collection is that each molecule is attached with a chemist, mostly affiliated with Boston University, who then identify a hit and then help you do medicinal chemistry and further optimize that. So that's an added sort of bonus of this collection. And so if you're interested in screening our collection, you can, our website's here, BU-biotech Oct. So this is another, we talk about decision making, choosing the number of compounds to screen totally relies on your bandwidth. So 4 million compounds, if you tried to run that in 96 well plates, it would take you 174 straight hours of screening. 1536 well plates, it's still 97 hours, because that's partially a consequence of the fact that the more dense plates take longer to scan. 40,000 compounds is going to be 17 hours in a 96 well format and 10 hours in a 1536 well format. So how much time do you have? How much reagent do you have? How will you be able to process a given number of compounds? And you really just want to choose the maximally diverse screening collection with a size that is adequately matched to your capacity to screen. That might be not very many compounds, but you want to make sure that if you are screening not too many compounds, that they are diverse. You can also purchase special collections, compounds full of known actives. This could be helpful in a phenotypic sense if you just want to identify a drug-level pathway that is linked to your target of interest. There's also really important to do for repurposing. So there's several known active collections you can purchase. And so the key qualities of the best screening libraries are that they're going to be diverse, drug-like, comport to what we call Lipid's rule of 5. They have adequate molecular weights, lipophilicity, hydrogen bond donors, and acceptors. And they're devoid of nuisance compounds. I've been going really slow, so I'm sort of running out of time. So I'm going to skip through a lot of this, the chemistry I have on nuisance compounds. But basically, nuisance compounds are referred to as PAINs, which stands for pan-assay interference compounds. And these are compounds that are chemically reactive or have poor physical behavior. They aggregate, they interfere with its detection spectroscopy, the ones that absorb fluorescence or absorb UV light, if that's your detection method. So I'm going to skip through all these types of chemical reactivity, basically, but you can have things that react covalently with proteins. You can have compounds that exhibit redox activity are going to interfere with alpha screening, that singlet oxygen that gets generated. Aggregation, I touched on this before, so this is a really common source of false positives where, typically you're looking for a molecule that specifically inhibits a binding site on a protein, so this is the ligand inhibiting the protein, and ideally the inactive compound is not going to interact with the protein whatsoever. Aggregation is a phenomenon by which the inactive compounds tend to belong together in this, these are organic molecules, and they sort of cluster together or aggregate together in the aqueous environment of the assay, and then that causes the proteins to then stick, the hydrophobic regions of the proteins will stick to these colloidal aggregates of compound. And sometimes this will look like, or have an inhibition effect, because the activity of this protein is then going to be blocked. The telltale sign of aggregation is the shape of the dose response curve when you measure dose response after a screen. So you want to have this nice sloping sigmoidal curve. And if you have a dose response curve that looks like an on-off switch, like there's just a certain concentration at which there's activity, and then you go down instead and there's no intermediate data points, that's a really strong sign that you're dealing with a compound that's an aggregator versus a specific inhibitor. And unfortunately, it's really difficult to predict aggregation. It depends on the compound structure, the assay conditions, the protein target, compound concentration. Super unpredictable. That said, there are websites where you can plug in your structure and it can tell you, yeah, this kind of looks like it could be an aggregator. Not super accurate, but it could be helpful. So there's also, I think I touched on this when we were talking about luminescence. Approximately 5% of compounds inhibit luciferase at 10 micromolar. That's a good proportion of the screening collection, 5%. Also, you want to keep in mind it doesn't necessarily reduce luminescence. A compound that interacts with luciferase might also stabilize it. That's going to result in increased luminescence. And we talked about, a good control is to use vanilla luciferase. And vanilla luciferase is an orthogonal luciferase. It has a different substrate. Really unlikely that a given molecule is going to inhibit or stabilize both of these two very different luciferase enzymes. Again, fluorescent molecules are going to impede fluorescence assays. Compounds that chelate metals are going to cause interference in any type of assay involving a metal, basically. And then there's molecules that also disrupt membranes, and they're going to they basically sort of insert themselves in the membrane, and so they could, if they do that, adjacent to a membrane-bound protein, they may look like they are inhibiting that protein when they're really just disrupting the environment of the protein. Of late, there's also this concern for these lipid disrupting molecules, phospholipidosis. So this comes out of recent screens for SARS-CoV-2, basically. Phospholipidosis is not a new concept, but recently in the antiviral screening setting, there has been a lot of screens of FDA-approved compounds to see if they inhibit SARS-CoV-2, so we could potentially repurpose an approved drug for antiviral purposes. And so this is an example of dozens of hits that have come out of these screens, dozens of approved drugs. And what was interesting about these hit lists is that they were very diverse compounds, very strange patterns. All of these compounds really have, most of them have known targets, and there's essentially no correlation between their known potency and their antiviral activity. But what they all do have in common is they've got like a basic amine and then a bunch of groups, so cationic and amphiphilic in nature. And so it was ultimately determined that they all share a common mechanism, which is phospholipidosis. It's disrupting the lipid homeostasis in cells. It does have a virucidal effect in cells. Not clear the exact mechanism. But the reason this is a problem is that it rarely occurs at the low nanomolar potencies we want to see from a drug. And phospholipidosis-based mechanisms have never been shown to translate from in vitro to in vivo activity. So for whatever reason, kills viruses really effectively in an HT assay, never has shown a statistically significant antiviral effect in a clinical trial. And so it causes a lot of, not necessarily false positives, but false hope and a lot of wasted effort and resources. So you want to avoid that. You want to counter-screen antiviral hits specifically for phospholipidosis, and there's a protocol in this journal here.
Are those cytotoxic or no?
Typically, in an antiviral assay, the hit is not going to be cytotoxic at the concentration at which it has a virucidal effect, but some of them are at the higher concentrations. But in general, it's an infection assay. We're looking for a compound that kills the virus without killing the cell. And then this is just some perspective. You know, a good percentage of drugs do have pains functionalities. They may be desirable depending on your target. But that said, I have a couple of really bad actors here that come out of hits all the time, very promiscuous in screens. Do not ever pursue a hit that has either of these two chemical structures. Avoid them at all costs. Okay, so lastly, in the last couple seconds, I'm going to just talk quickly about the process of hit triage and validation. So you have to decide in your assay what is a hit. You have to define a cutoff, basically. This could be this is an arbitrary predetermined value. You could say all compounds with 70% inhibition at 10 micromolar. You could apply a more rigorous statistical analysis. You could say all compounds with activity that's 3 standard deviations from the mean. That could be your threshold. It could also just be determined by your bandwidth. Maybe this produces more hits than you're able to prosecute. So you could say the top 50 compounds, basically, based on activity. However you define a hit, there's inevitably always going to be false negatives and false positives. Basically, the hits and the non-hits are overlapping always, and the number of false positives, false negatives, the proportional number just depends on where you draw that line, basically. So step 1 in validation, perform QC check on the assay. We talked about that. Do a Z-factor calculation on the assay. That tells you if your hits are really hits. You're going to do a QC check on the sample. You want to make sure that the hit compound in that well is really what you think it is. You're typically going to engage a chemist in this, use LCMS or NMR to confirm that. It's best to replicate that activity with a fresh sample not coming out of that plate, because you don't know what people put in that plate. You're just trusting that someone put that molecule in the well, but it's best to independently confirm the activity with something procured from somewhere else to make sure the activity is reproducible. And then you're going to counterassay for possible artifacts. You want to make sure the observed activity is real. We've talked about a number of different pitfalls, and so you want to just test against those things. And then you always want to have a plan for a secondary assay that's orthogonal for the same activity, completely different reporter. If you're using fluorescence, you go to luminescence-based assay. If you're doing an FP assay, you can do SPR measurements. And it's important to keep in mind the secondary assay does not have to be a high throughput assay. It could be a very low throughput, resource intensive assay. But you just want to make sure that it's complementary to whatever you're using to ensure that your hit is not just an artifact of the detection method in the HTS. And then step 3, check for dose dependence. You want to make sure that the compound behaves with a nice sigmoidal dose response curve, because that's what you want a drug to do. That's how you want a drug to behave. If it doesn't, it might be interesting that it has activity, but it's not going to be helpful therapeutically. And then you're going to do some medicinal chemistry triage. You're going to make sure that hit compound is a good starting point towards new molecules. You want to check the plates for similar compounds. This is also an instance where you're going to recruit a chemist. Were there similar compounds to this on the plate? Were any of them active? Were all of them dead? If you have 200 of a given chemical scaffold and only one of those compounds was active, that's not a great starting point because it tells you can't really do medicinal chemistry. You can make changes to the scaffold, you're going to lose the activity. You also want to assess how difficult it's going to be to get my hands on analogs to do further optimization, either make or buy them. And then it's also good to check, whether compound or compounds that look like it already have other activities, because that can give you a clue as to the mechanism. And then the next step is medicinal chemistry. So this is my last slide. This is just to give you some perspective of, these are all FDA-approved drugs that were originally discovered based on a hit in an HTS screen. And you can see the time period between the screen and the year that the drug was approved is often 10 years. You can also see the evolution of the structures. They changed quite a bit over that 10-year period of medicinal chemistry optimization and then clinical trials. And so really the screening hit, it would be great if we could just identify drugs out of a screen, and you can do that with the FDA-approved compound set. But if you're not working with that set, you're typically looking at what is a starting point towards a therapeutic, but not the actual drugs. There's going to be a lot of medicinal chemistry between the screen and then the final approved drug. As I said, I never have time to go through the pitfalls, but these slides will be on the website or on the Blackboard. And it's basically, common things you run into. We've touched on all of these as we've gone through the different principles. So with that, sorry, I went a little bit over. Are there any questions? Okay. All right, well, thanks, you guys.
Thank you.
Thanks so much. Okay, so while we set up the second lecture, I'll be able to keep my announcements since there's more people now in class at 8 o'clock. Hey, Lauren, did she take her slides? Okay, so let's.
Thank you for seeing.
Oh, yeah. I'm not sure if it's close enough.
Oh,
Okay, so all you need to do is
there's actually an outlet over there. It's not almost at the side.
I think that it's on back. So just move it off your flash. So just to be sure about next week, because I was here at 8 and some of you straggled in after at 8. We will be having I will post the midterm after next week's lecture, okay? So that's the last set of lectures. You'll have 2 weeks to do the midterm. I will post instructions for the midterm early in the week, okay? It's a take-home. You have 2 weeks to complete the midterm. So, and I will repeat the instructions, but to reiterate, do not get somebody to help you do it. You work on your own. Content can be looked up from the internet. You can use illustrations. Do not cut and paste. If you find information from the lectures or the internet, it's all right to paraphrase it. It means that you understand the content and you're answering the question, but don't copy. That's plagiarism, okay? Okay, and we will find that, and we will tell you about it, and then you'll lose the credit for the course. And I had this happen maybe twice or 3 times over the last 10 years, and believe me, you don't want to go through a disciplinary action with GMS, okay? So if enough of you want to do a review of the salient points, I'm happy to do a Zoom at the end of one of the days during the week, next week. And I'll add that to my email, and you have to get back to me. I can't do individual review. I'll make a common time. It can be at the beginning of the day or the end of the day, that we can all come together, as many as possible, to do a review. Does that make sense? Would that be useful for people, just to hear what the questions might be? Okay, so would something around 5 to 6 work for most people?
Well, what day are we talking about, sir?
Tell me what day would work if it's 5 to 6, and I'll make myself available.
I think midterm review.
Okay, what day works? What other lectures do you have during the week? You know your schedules.
Or I think Wednesday would work for me, 5 to 6.
Would Wednesday work for most people? Okay, then I'll post a Zoom link for Wednesday, and I'll make myself available to answer the basic questions about what the content of the test will be, okay?
Is it going to be recorded?
No, I can record it, but what good is a review if you're not there to ask them questions? It's kind of a wasted amount of time. Yes?
Can I actually just ask a quick question about the final? I was just trying to figure out my plans for going home for the holiday, and it looks like we have 2 days for it, it's December 10th and 17th.
Yes.
Do you anticipate using both days for presentations based on the class size?
Well, I think I'll have to look at the final number of students.
Mm-hmm.
Per student pair that are the presenters, we have 20 minutes per pair.
Okay.
So we have 180 minutes. So in theory, we can do about 9 pairs in the 180 minutes. It never works out, it's more like 8 pairs because so we will be using both both weeks to do the oral presentations.
Okay, yeah, I gotcha, thank you.
Does that make sense?
Yeah, I just wanted to double check.
Okay. Yeah. So I think that Dr. Bragdon will go through the lecture on RNA now. And like I said, we'll plan on Wednesday 5 to 6 for the session review, okay? And, okay, and remember that just as a reminder, participation, BU requires live classes. We're not recording. I do post last year's recording. The lectures, the content changes slightly, but it's a freebie to come to the lecture, at least for half that 10 points that is for class participation. The other 5 points is dependent on if you're asking questions and participating. So don't give away at least the 5 points of coming to the class, okay? I can't make you participate, but it's there as part of the grade, okay? So just be cognizant that there's 10 points there on the table for coming to class, okay? Okay, I'm going to go back up. Deb?
Yeah, thank you.
Professor, excuse me, I have a question. It's in general relation to attendance to other classes, like international students like me. We have this requirement that we need to show that we are attending classes, but I noticed that classes are not taking attendance. Do you know what I could do, or what option can I take in that case? Because I need to report that I'm actually going to classes.
Yeah, I mean, I come to every lecture.
No, I'm talking in general. I know you are in you see me, and this is a small group.
Yeah.
But for example, biochemistry, where we are like 500, or I don't know.
They'll just, provided that you are matriculated for the program, they will write you as president, okay? Because I know the larger classes, biochemistry, are recorded and people do the master.
No, I'm attending.
Yeah.
But I need some kind of proof. Like,
Yes.
if you could guide me on what I can do
I
to
would,
get.
I would talk to the individual lecturers for your class. Raise that question. I can only address my class.
Okay. As advice, I thought maybe you could like give me. All right.
Thank you.
Thank you.
All right, so today I'll talk about a little bit about RNA, what we can do with it, and I'll have an example of how I actually use it in my own. Quick question, has anybody used RNA in the past? That's generally what I have seen, but this may be a little boring for some of you, is what I've found, but just bear with me and we'll get through it, hopefully quickly. So a quick outline for today, we'll talk about what RNA is and why we use it. We'll look at, I like to highlight the RNA isolation because if you can't isolate it, then you can't look at it, right? You can't analyze it. So that's a really important part. We're going to talk a little bit about the theory of hybridization. That's how we actually look and use the RNA. We will look at some principles of assessing the expressions, and some techniques, approaches, and the analysis. I don't want to discredit, but I would say a lot of these techniques I think are a little bit older. So you may not run across them quite so much, but it's good to have a basic understanding of how it all works and really where the technology is moving forward and what it's based on. And then I also, hopefully we'll have time, and so I can show you a little example of how we use RNA work in the lab to look at gene expression. Let's see. So RNA is just ribonucleic acid. It's similar in structure to DNA. There are different types of RNA that's in the cell. We have messenger RNA, which is what we're mostly interested in, ribosomal RNA, and transfer RNA. The messenger RNA transfers the information from the genome into proteins, which is by translation, and is why or at least what I'm mostly interested in, because I want to see that transfer information to the protein level. Quick image just so everybody's familiar with the RNA, which I hope most of you are. So why do we use RNA? Well, every cell in the organism contains the same set of genes. However, only a fraction of those genes are used at any given time within any given cell. And so this careful controlled pattern of expression is called gene expression, and it's highly dynamic. So what do you think when I say dynamic? What do you think that means? Exactly. So over a course of time, that gene may be turned on, may be turned off, maybe the expression goes even higher or lower. But across time, what else could we look at? What else would be important to look at that's associated with time? What is the gene first and then second? Yeah, we can look at different genes and see how they play off from each other. And across time, we can look at development. How does this, like a stem cell differentiates? That's what I'm mostly interested in. So we can look at different gene markers. So is this cell, I'm in orthopedics, so I'm with Dr. Griswold. So is the skeletal stem cell a stem cell, or is it now a progenitor cell, or is it an osteoblast and chondrocyte? So we can look at different gene expressions. So we get very dynamic. I'll show you what we look at across time, differentiation. And I'm interested in injury. How does injury affect the expression of certain genes? And then a protein cannot be in the cell or a tissue if the mRNA is not expressed. So that's why we look at gene expression. We can look at proteins or genes, but without the gene, we're not going to have the protein. So we start at the beginning. And then RNA can be used by researchers to determine which genes are turned on and when. So what we were just talking about. So currently the analysis of RNA expression is one that's mostly used. And then these are the different types of information we can get from mRNA expression. We can identify tissues that express the gene, right? certain tissues should have high expression of certain genes. So chondrocytes are cartilage associated, so they should express high amounts of cartilage. We can look at quantitative levels. So can we look at, is the gene upregulated, downregulated, and when? The temporal relationship is also another key point for my research. And then 4 and 5 is not really what I looked at, but you can look at the structural information about the mRNA, so the splice variants, as well as post-transcriptional levels of regulation. And then I do want to add a caution. So I do use a lot of RNA gene expression data in the lab. However, just because it's there and it's highly expressed does not necessarily mean that it's going to equal the amount of protein, right? So I like to use gene expression because you can look at a lot of different genes pretty quickly and easily. However, we always follow it up by looking at protein. So just because a gene is upregulated doesn't necessarily mean the protein's there and it's actually doing anything. There are different methods of isolating RNA. We use the Trisol method primarily in the lab. This is a guanidine phenol extraction followed by a PCP extraction. You can also use chloroform, and then that's followed by the alcohol precipitation. This is the classic gold standard. It's widely adopted and used, but it does lack throughput. It takes about 2 hours to extract the RNA. Depending on your tissue, I don't recommend a lot of extractions at one time. You really should just do a handful at one time. So if you have 100 samples, it could take you days and weeks to get through them all. There is the glass fiber filter. Again, this is the guanidine alcohol extraction followed by the glass fiber filter cartridge. This is great for cleanup. It's easy, it's high throughput. We use it if we're going to use, say, RNA sequencing or microarray. Following extraction, we will use these filters for cleanup. But you can have filter clogs, so you would lose some of your material. It can be inconsistent, and there is some cost to it, more so than the Trisol. Again, about 60 minutes to do it, so it is quicker. And then there's the magnetic beads. Again, it's a guanidine alcohol extraction. However, you use magnetic beads to extract the RNA. These are simple, high throughput, very sensitive in consistency. I would say the disadvantage would be probably cost. Buying all those tubes, and then you have to have the magnetic feature. But they are really quick, they're 30 minutes. So if you have hundreds, thousands of samples, this is probably worth the investment. So this is the Trisol method. This is what we use in the lab. You have your starting material, your cells. You do have to homogenize the tissue and cell lysis. We do this through guanidine phenol extraction. It's the phenol, so it's pink. We call it peptobismol in the lab. But you have your RNA, your protein, and DNA just floating around. This is what it actually looks like. We do a phase separation. So those who have taken chemistry will remember these phase separation. You have aqueous, non-aqueous layers. Again, you have your organics on the bottom, it's pink, it has your proteins and lipids. You have this interface, that's where your DNA is located. And then your aqueous phase is at the top, and that's your RNA. So we take that aqueous phase, precipitate that using isopropanol, spin it down, you have a nice RNA pellet. Fingers crossed that you have a pellet that you can see. It's not always guaranteed, you may not see it, but it is there. Tell students, just because you can't see it, it's most likely there, it's just not very visible. Then we do wash it with some ethanol, and then we resuspend with just a water or TB buffer. Yeah?
Oh, sorry, is the DNA in the white interphase, or is it in the organic phase at the bottom?
It's mostly in the interface.
Okay.
And so when you do the extraction, it's important to avoid that interface. So I usually tell students, if you're getting to that interface, just leave that little layer. Try to get as much as you can, because that's your material and you want that. However, you don't want it contaminated by DNA. So leave it, it's okay. Glass fiber filters. So this is widely used method for high throughput RNA isolation. It uses a glass fiber filter plate. This is where RNA can bind to and filter. It's due to the high salt and alcohol concentrations. You can avoid the phenylchloroform extraction, so you don't have that contamination, and you can allow for the automation. So it's just spinning your samples through the column, basically. I did find this neat publication where they had the columns that they purchased, and they tried to find ways to repurpose it and use different filter papers they had in the lab to extract the RNA. And I don't know if I would suggest that per se, but they were able to recover a lot of the RNA using just a filter paper or the bottom paper in the lab. Lastly, we have the magnetic beads. Again, we have our lysis of tissue and lysis of cells. We have binding to the beads. You wash the beads to start to supernate. So this is where you have your magnet for your beads to keep them in the tube. You wash and elute, so you're removing the RNA from the beads. Remove the beads, resuspend, and then you have your RNA in your tube. So it's quick and easy. Yeah, it's nice, but we don't use it because it does cost more money. So RNA isolation. So I saw a lot of hands go up that have worked with RNA. Did you guys also isolate the RNA? Did you guys have any issues with RNA? Yes, it can happen. Depending on your tissue type, it can be very tricky to get that RNA out. How about you two? Did you guys have issues? Yeah. So, you know, the more you do it, usually the better it gets. You find little techniques that help you and the lab. So some of the reminders that we have is that RNA is very unstable, and there's RNases everywhere. So we try to isolate our RNA in undegraded form. Can you imagine why we want the undegraded form? If it's degraded, it's not there. We can't use it. You know, if you use an assay, your results are wrong, and so there's no point in doing it. And so we definitely need it in a good quality amount. So we always work on ice cleanly and quickly. So these are just the practical considerations that I have in the lab that I always tell students and try to remind them if they do run into any problems. Number one is work quickly, which I know can be difficult when you're first starting. You know, a lot of times you're fumbling over materials, trying to find things, but really practice makes perfect on this one, so work quickly. This includes your tissue isolation, extraction, and again, limit the sample number. So for my lab, we extract RNA from tissue from mice. So we euthanize mice one at a time. We euthanize all at once and then extract the samples. We do one mouse at a time, or tissue at a time. We then put it into a tube and flash freeze it into liquid nitrogen as quickly as we can, so we know that it's not degraded at that point. And then during extraction, we do limit the number of samples. So if you're learning in the lab, I really restrict you to probably 2 samples for your first day. If that goes well, then you can go up to 4 or more. I usually don't like to do more than 8, and I feel really confident in my techniques. So that's what the Trisol method. It's really important to limit your samples. Also working on ice, so our tissues are stored at -80 at all times, which can be problematic depending on storage, and you can lose electricity, but that needs to stay cold. Otherwise, the RNA that's inside the tissue will degrade your RNA. And then extraction, the first steps of extraction are always done on ice. We use a tissue lyser, which is just mechanically disrupting the tissues. We actually freeze most parts, so our samples stay cold during that process. Then we need to work cleanly. We always wear gloves, which you probably should be anyways in the lab. It's a good reminder. We do use RNase-free solutions, so we can use filtered autoclaved water. You can also use RNase inhibitors if you need to really inhibit any bleeding. So, like if we run into a problem that our extraction's been working very well, but now all of a sudden it stopped, we do have solutions in the lab that we can spray down the benches to help with that. Also, RNA integrity, so we have to make sure that it's not degraded. It needs to be good quality, otherwise our results are wrong. There's no point in doing the research. So the first step that we do is we run our RNA on an Arduous gel. 1 to 2% Arduous is fine. We are specifically looking at the 28S to 18S bands and estimate the ratio. But it's highly subjective. We don't quantify these bands. If they're there, we move forward. If they're not, the sample's lost and we start all over again. If you're doing more microarray type analysis downstream, the core would require the RIN, which is the RNA integrity number. They would do that for you. However, it needs to be a good high number. And I'll talk a little bit more about that next. First is the Arduous Gels. This is a typical gel when we run RNA. Top band is our 28S, bottom band is 18S. As you can see, 28S band looks bigger, like more intense than an 18S. So we say that's a good quality to move on. You want the ratio to be, you want 28S to go double the amount of 18S in the perfect world. So the RIN number, this is capillary gel electrophoresis. It uses both size and time to calculate. It's all on the computer and software tool. Really estimates your RIN number, so you take away that subjectivity. It's more robust and it's more reproducible. So this is what the gel looks like. So this is intact versus degraded. This is our ideal. You have your 28 to 18S bands. As it becomes more degraded, you have more bands and they're smaller in size. As we're over here, we don't even have 28S or 18S really left. So the software will then look at the fluorescence or the intensity of the band across time, look at the peaks so that it knows where the 18 and 28S peaks are located, and it will find the area underneath the curve and give you a RIN number. A RIN 10 is perfect, and you're really good. That would basically be this very first column. Partially degraded would be a RIN of 5. As you can see, 18 and 28S are there, however, the ratio is not correct, and you have a lot of smaller sizes that came off quickly. And then fully degraded, you can see the peaks are completely gone. I would say, a RIN of 8 or above is good. Anything below that, you would really need to talk to your core and see if you can clean it up a bit.
Can you just talk a little bit more about what these peaks actually are? So these are ribosomal RNAs?
Yep, it's ribosomal RNA, the 28 subunit and the 18S subunit.
And you would use that because that's obviously in any cell you're looking at. All right.
Yeah. It gives you a good idea of what the quality of your total RNA is. Because if this is degraded, then your other RNA will not.
Gotcha. Okay.
Any other questions? All right, so how do we analyze RNA? So this is all based on the theory of hybridization. I assume, but I like to ask, everybody understands hybridization, like the whole process. I think you've probably seen it multiple times. But if you have questions, ask away. So we have our double helix strands over on the left. We add heat, it starts to unwind, you have denaturation. You add more heat, it's completely separated. When you cool the temperature, we have annealing or renaturation. You have your double helix